Okay, it's recording now, so let's try not to say anything crazy. I don't want to get in trouble. I tend to get in trouble a lot these days. Okay, so we're going to continue with what we were talking about back on Wednesday last week. It still says Lecture 2 on your PDF notes, but we're on Lecture 3 now. And if it really bothers you that we're doing Lecture 3 and your notes still say Lecture 2, I can give you a PDF that says Lecture 3 if you'd like. Let me make sure that I have this thing on writing mode real quick so that we can get this. I can do examples for you. Woohoo, that worked. Okay. All right, so let's get started on the lecture for today. And I know we wanted to do some, what's it called? Lecture on configuration, but like I said, we'll do that on during discussion today at 1 o'clock. You didn't have discussion on Monday last week, but we will have it today because you have a quiz during discussion, which you'll take on your own computers on Blackboard, and then you'll also do, and then after that, I'll do the electron configuration crash course for you, and then also there'll be the assignment. You'll have an assignment assigned. Hopefully, if we get through this today, you have an assignment assigned, and once you have the that clock says 9:30. What the hell? Once you get when the assignment is assigned, you'll be able to work on it in discussion if you want to work on it in discussion, or you can work on it on your own. I don't really care where you work on it. It will be due by the next class period, which is Wednesday at noon. Okay. All right. So. Well, we left off on Monday talking about the octet rule and valence electrons and all that stuff. All of that comes down to what we have here, which is the number of bonds that a certain atom can have, okay? So if you recall, fluorine, which is a group, notice I used green laser today. It's a little bit easier to see. We have all kinds of lasers actually. I can get a yellow one too, but that'd probably be even worse. But remember, fluorine here is in the halogens, and the halogens have 7 valence electrons, right? That means they need one more electron so that they can have a full octet and be happy. They can achieve that electron just by having one bond with something else, right? So here we have hydrogen fluoride, right? And hydrogen fluoride, actually, you put it into it can actually become an acid if you put it into an aqueous solution. So for everything that's a halogen then, right, all it needs is one bond, and it can only form one bond, right? So also with the same thing with bromine too, right? And you saw that with salt last week, right, with the NaCl. It has formed one bond with chloride, okay? So for those halogens, that's how it goes with them. So the next group over is the chalcogens, right, which starts with oxygen group 6, right? So remember that oxygen and everybody in that group on those valence electrons have 6 electrons. They have 2 lone pairs that don't do any bonding at all, and then they have one pair, one electron here or one electron there that is for bonding. And so for something like oxygen, it needs 2 things to share electrons with for it to gain an octet. So here it shares 2 electrons with a hydrogen, another hydrogen. Now it's got its octet, right? And you've made yourself water, okay? Next on the periodic table, we have nitrogen, the group of nitrogen, right, which is group 5. Group 5 has 5 valence electrons. One of them is a lone pair, okay? One of them is a lone pair. But then you have 3 that are not bonded at all and not in a pair. And so for it to have its full octet, you have to have 3 bonds to it. And it doesn't have to be nitrogen, or hydrogen rather. It could be anything that has a single bond bonded to it, right? So hydrogen's all the way around. And so now it's sharing 2 electrons here with hydrogen and nitrogen, 2 electrons here with hydrogen and nitrogen, 2 electrons there with hydrogen and nitrogen, and then a lone pair, and that gives us an octet of 8, right? That gives us an octet of 8. And then the last one here that's probably going to matter to us, well, we'll go a little bit further later, but for this is carbon. Carbon has 4 bonds, right? Because it's in group 4, right? And so none of its electrons are paired already. They're all single. They're all available for bonding. And carbon has 4 bonds, so it needs to have a bond with 4 different atoms: hydrogen, 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 hydrogen. All of them shared, and now carbon has its full octet. So the moral of this story is that as you go across the periodic table from right to left, right, you successively need more bonds, right, to get to an octet, right? So let me ask you a quick question. I'm not even going to put it up for you to scan, just out loud here. How many bonds do you think boron's going to need to have a full octet? It's a trick question. It's actually a trick question. The reason why it's a trick question is because boron is in group 3, which means it only has 3 valence electrons, right? So it's one of those that doesn't do the octet rule. It can only have 6 electrons. It doesn't have enough, right, at all. So that's actually a trick question. We'll talk more about that later. All you need to remember, though, for this point is from fluorine to carbon, right? From fluorine to carbon, as you go across, you need successively more bonds to get to carbon with 4 bonds there. And carbon, of course, is got so many bonds that it can bond with many things at the same time, and that's why you have such a diversity of things with carbon, like candy, DNA, proteins, fats, all kinds of stuff. This table here is made of carbon, right? Charcoal is made of carbon. So many things have carbon in it because carbon has so many bonds that it can bond to it, right? This is actually called ammonia, right? It's the same stuff that's in your, you spray your glass with to clean your glass, and I think that's water. No, I'm just kidding. That is water. But the point is, they're trying to get to nearest. They're trying to get to the noble gas configuration, which is 8, and so that's how they do it. They achieve it by having bonds, right? In addition to their lone pairs. All right. So this is your first question. Go ahead and scan it. I found out that you actually have to be on the Texas Wesleyan Wi-Fi for it not to ask you over and over and over again to sign in. So make sure you sign in on the Texas Wesleyan Wi-Fi. And then don't forget to do this too, because this is how I'm taking attendance. I'm sad that 2 of us aren't here today. Hannah and Mary aren't here today. So sad. All right. So 6, 9, 11. So we'll need 11 responses before I switch it over. So far we have 6. We have 9 so far, so 2 people haven't responded yet. Disconnect from the Wi-Fi and connect again. I found that helps actually. And then reconnect to it. And then log into the Wi-Fi. Wait, did you get the secure? Registered?
That's weird. It didn't make me do this last time.
That's so weird. iOS device? Yeah, the second one. What the heck is that? I've never seen that before. Continue. Oh, that is so weird. Cancel it out. Do the yeah.
What about this one? Should I do the secure?
You can try that one, but I don't know what the username and password is for that one. Maybe it's just your username and your password again.
Yeah, try mine.
I've never used that one. I've always used the registered one. Is anybody else having problems logging on? Oh, there you go. Trust. I mean, it says secure.
It looks pretty secure.
Yeah. It did say secure. Come on, you can do it. Come on. Come on, Wi-Fi. Well, something's connected. To get out of it and go home. It says you're connected to it already. It just didn't it just didn't show the check mark for some reason. Okay. Did it work?
Yeah.
Okay. All right. So let's see what everybody said. 11 responses. Ooh, wow. I didn't realize there would be so many different answers here. But the good news is the vast majority of you put A, which is one bond. All it needs is one bond, right? Well, why is that? Exactly. It's in the same group as fluorine, right? Remember what I said last week? Whenever you're in the same group, you actually react the same way. You have the same trends. So if you have fluorine and you have chlorine in the same group, they're both only going to need what? One electron to be a full octet. And if you only need one electron to be full octet, you only need what? You only need what? One bond. So the answer there is one bond. Good stuff. All right, let's keep going. I'm not going to make you break up into your teams and talk about that one. That's just a number. Unless you want to talk about it. I'm kidding. We don't have to do that. But we will do that eventually. There will be some questions like that, though. All right. Oh, wrong keyboard. There we go. Okay, so like I was talking about before, right, we have both lone pairs and bonding pairs of electrons in Lewis structures, right? So you take a look at water here, right? Before you saw water with a line between the O and the H, right there and right there, right? But really what that line represents is a bonding pair of electrons, right? One of these electrons belongs to the hydrogen, one of these electrons belongs to the oxygen. And so that's called a bonding pair. But then I said already before, but just as a little review, we have lone pairs right here too that don't do any kind of bonding at all, okay? They don't do any kind of bonding at all. So for example here, we can put two oxygens together with a carbon and get this molecule here. Does anybody know what that is? Carbon dioxide, right? So the thing about it, though, is, right, carbon in the center has 4 electrons that it can bond with something else. Oxygen has 2 electrons and 2 electrons. So it kind of works out, right, where one of these electrons bond with this electron bonds with that electron, right? And then this electron here bonds with that one, and that one bonds with that one, whatever, whichever one hasn't been taken up yet. And it can make carbon dioxide, right? The point is that, though, since on one side there's going to be 2 bonding pairs of electrons, right, like this and like this, that's actually a double bond, right? It's not a single bond like we saw before, right, in the first slide that we saw, okay? So sometimes 2 pairs of electrons need to be shared. Here are 2 pairs of electrons there and 2 pairs of electrons there, and those are called double bonds, okay? Those are called double bonds. You can go a step further, right? If you have 2 nitrogens together, that's actually called nitrogen gas, or N2. Nitrogen in itself has like 3 bonding electrons, and so you put two of them together, and then each one of these can pair with each other, right, and make a bond. And now you have 3 pairs bonding with each other. And what do we call that? We call that a triple bond. So the thing I want you to know about this is that as you increase the number of bonds, the bonds get stronger, right? The bonds get stronger, number one. It makes sense because the more bonds you have, the stronger, the connection is. It's harder to break those. But then also, as the number of bonds increase, the distance between the atoms gets shorter, okay? So you have a single bond, and it's a little bit it's farther away from each other. You get a double bond, it gets closer to each other, right? And then a triple bond, it gets the closest to each other, the 2 atoms are, okay? So, and then the other thing also is that as you increase the number of bonds, the bonds get stronger, okay? The bonds get stronger. So when we form these bonds, right, that are sharing electrons, we'll have to talk about its polarity, okay? We have to talk about the bond polarity, which is the measure of how equally or unequally shared the electrons are in the covalent bond, right? And remember, whenever we're forming these bonds, sometimes it's with super electronegative atoms over here, like the ones that are in the halogens, right? And what are electronegative atoms? What do they like to do? They like to steal electrons, right? Remember what I said about chlorine? Chlorine's so bad, it steals electrons from kittens, right? Right? They used chlorine during World War I to kill soldiers, right? To make hydrogen chloride gas in their lungs, right? And it burned out their lungs because chlorine is so bad. It'll take an electron straight from the water inside your lungs and make hydrochloric acid in your lungs if you get exposed to chlorine. So if you pair chlorine with another atom that's not quite as electronegative, what does that mean then? Chlorine is going to take most of the electron density away from that less electronegative atom, right? So here you have fluorine gas, right? F2. And since these both are equal in electronegativity, right, they share the bonds equally. They share the electrons equally, right? There's a push and pull between the electrons, but they have the same strength, so it's not going anywhere, right? Whereas when you have hydrogen fluoride, right, what's the trend? The trend is as you go to the right of the periodic table, the electronegativity gets higher. Fluorine's at the far right. Where's hydrogen at? The far left, right? So, does hydrogen even have its electron anymore at this point? Fluorine's pulled it all towards itself. And that's why you can see here in this electron density map, right? Hydrogen is more positive and fluorine is way more negative, which makes sense too because on the periodic table, things that are on the left side are what charge? They're positive anyway, right? They're positive anyway. So when they come together with other atoms that are more electronegative, of course they're going to go ahead, hey, fluorine, take my electron. I'm positive anyway, right? So that's the easy way to remember it. Look at lithium fluoride, right? Lithium fluoride, same thing over here, group 1, right? Lithium is a metal that has a +1 charge. It's already positive, right? Just like sodium was, right? So as you go across our table, the halogens are the most electronegative, so fluorine is there. It's taken most of the electron density for itself from lithium, and that's why it's mostly electronegative on that side or negative on that side with electron density, and then it's not on the lithium side because lithium's positive, right? So that brings us to these two vocabulary type of terms that you need to know. We have the nonpolar covalent bond, and we have the polar covalent bond, right? So the polar covalent bond is exactly what we were just talking about. It has two different poles, right? One side is plus, and the other side is negative. Hydrogen fluoride, lithium fluoride, right? Plus on one side, negative on the other side. Plus on one side, negative on the other side. Kind of like the poles of a magnet, okay? Magnets are positive on one side, negative on the other side, right? But fluorine gas, though, is it positive or negative on the one side? No, it's actually the same all the way around. So fluorine gas, or F2, is a nonpolar covalent bond. Does that make sense? Okay, that's a nonpolar covalent bond. All right. Next question. Mary, do you have a mask? Okay. You need to put it on. Security will have my, if not everybody in my class has a mask on. So, which molecule has a polar covalent bond? O2, H2, HCl, or Cl2? Go ahead and log in, and or most of you have already logged in. So, Mary, I'll give you a chance to do this one so that I can count you here for today. You don't have to get it right, obviously, because you missed what I said just before this slide. But I'm recording it so you can get it later on the video.
Okay.
All right, which molecule has a polar covalent bond? Let's see where we're at. So we have 12 now. Uh-oh, I lost it. Oh, there it is. Okay, we've only got 9 responses. 10 responses. We still need 2 more. 2 more people. 11 people now. So 1 more person. Or am I miscounting? No, I'm not miscounting. Okay, they're all in. Let's take a gander about at the distribution. All right. T said O2. 1 said B. I forgot what B was. 8 said hydrogen chloride or hydrochloric acid, right? And D said the other. I can't remember what the other one was either. All right. So, here it is. It's chlorine gas. Okay. So remember what I said, right? If you have like I'll switch it back to the PowerPoint here. I will say most of you got it right. It's hydrogen chloride. It's hydrogen chloride. But remember, right, what's the pattern that's happening here? Okay? If you have a nonmetal with a metal, right, a nonmetal with a metal, especially a nonmetal that's a electronegative, it's polar covalent. Okay? But if you have 2 of the same thing, it's almost always what? Nonpolar covalent, right? So in this question here, right, you had O2, right? Oxygen is pretty electronegative, that's true, but it's bonding with itself there. So it's going to have the same polarity on both sides, right? Same with hydrogen gas, same with chlorine, right? Because chlorine is the same thing, it completely acts the same way as chlorine does, right? They're in the same group, right? So you have 2 chlorines together, it's also going to be nonpolar covalent, right? So the only polar covalent bond here is which one? It's hydrogen chloride, okay? Hydrogen chloride. All right. Oh, dang, I was supposed to let you talk about that. Oh, well. Oh, well. Okay, so, but most of you got it right anyway, so there's really no reason to talk about it. So, as I alluded to before already, as you go from the left to the right on the periodic table, right, you get more electronegative. The halogens are the most electronegative, right? You would think that the noble gases are the most electronegative because it's the farthest to the right, but why aren't they electronegative? Exactly. Their octets are already full. They don't need any more electrons. They're quite happy the way they are. So just again, this is the formal definition of electronegativity. I keep on talking about it, but here's the formal definition. Electronegativity is the ability of an atom in a molecule to attract electrons to itself, right? But I've been saying, though, that going left to right makes you higher electronegativity, but it's also going up, from bottom to up, also gives you higher electronegativity as well, right? So quite literally, then the most electronegative atom on the periodic table is what? Fluorine, right? It's fluorine. So the more you go up the periodic table, from bottom to up, the more electronegative it is. And the more you go to the left to right, the more electronegative it is, okay? So you can see here in the periodic table, like these things here are the most electronegative. Nitrogen, oxygen, fluorine, and chlorine right here, right? Because they're the uppermost right-hand side of the periodic table, not including the noble gases, right? Not including the noble gases. All right. Yes? Oh, I'm not going to make you memorize all those things now. If I ask you a question about it, I'll tell you about it. Like, I'll tell you what the numbers are. There's no, didn't I say this last time? I have this philosophy, and that is you never should have to look something up that you never should have to memorize something that you can look up easily. All right, so what does electronegativity and bonding, what are the implications in bonding, right? It turns out that you can use the difference in electronegativity between 2 atoms to determine whether or not those 2 atoms are, in fact, sharing electrons equally in a covalent bond, sharing electrons unequally in a polar covalent bond, or they're just transferred electrons and it's actually an ionic bond. So I will give you numbers, you will have to figure out whether or not these atoms are, right, polar covalent together, transferring electrons together, equally shared together, unequally shared together, all those different kind of things, okay? So, if there's an electronegativity difference, right, between the atoms, so when I say difference, what does that mean? You take the numbers, right, and you combine them with each other, right? So it's like a +2 and a -1, right? What's the difference going to be? It's going to be 1, right? So an electronegativity difference between 0.0 and 0.4 means that it's a nonpolar covalent bond, pure, right? Equally shared electrons. Know that right there. Know that this means this and this right here, okay? Next, between 0.4 and 2, in electronegativity difference, right? That means that you have an electron shared unequally. It's a polar covalent bond, right? And if you get a difference between those two, that's what you're going to have, right? A polar covalent bond and electron shared unequally. But they're still shared, and they're still covalent, right? Still covalent bond. And then last but not least, atoms that are ionically bonded to each other, like sodium chloride, right, or lithium bromide, right, they are ionic bonds. They have electron transfer. It's not sharing of electrons, right, and it will have an electronegativity difference between 2 and 3.3, okay, between 2 and 3.3. Okay, so when two atoms share electrons equally, right, they have a polar covalent bond results, right? Unequally, a polar covalent bond results. So we have a very special designation for that, okay? For example, in hydrogen fluoride, you'll see things like this, where you have the hydrogen bonded to the fluoride, right? And you'll have this little lowercase, if you didn't know, that's a lowercase delta, right? It's a Greek delta letter, and it's lowercase, right? If you didn't know, a big triangle like that is actually an uppercase delta in the Greek alphabet. So whenever you see an uppercase delta from the Greek alphabet in science, it always means change in something or difference in something, right? That's why that's the change or difference in electronegativity, okay? But this is lowercase delta here, and lowercase delta here means partial positive, okay? And then, partial positive with a plus sign. And then lowercase delta with a negative sign means partial negative, okay? Those are the phrases that you need to know. Partial positive, partial negative, okay? And then you can also show it this way too. You can see that there's a plus sign, right there, signifying what the partial charge of the hydrogen is, right? And the electrons are going in that direction from the positive, right, towards fluorine. Okay. When you get to OChem 1, which would you be taking OChem 1 in the spring, right? You're going to be doing a lot of the partial positives and partial negatives, okay? Because there's not a complete transfer of charge here, okay? Unlike with what? Ionic bonds, where there is a transfer of charge, right? In ionic bonds, the electron from lithium, for example, is going straight to the fluorine, right? Giving the fluorine the extra negative charge, giving the lithium a positive charge, right? That's an ionic bond. But this is a covalent bond, right? And so if there is a polar covalent bond, there's not a complete transfer of charge. The electrons are just kind of flowing in that direction because fluorine is so electronegative. Okay? All right. Next question. So that one would be What are we on right now? Electrons, maybe? Yes. We have 7 responses. I've got 10 responses so far. We're still waiting for 2 people. Well, you having problems?
Can't change it.
No. Sorry. But don't worry, no one knows who did that except for me. But my opinion probably matters the most. So, okay, let's switch them over, see what everybody said. All right. Luckily, the vast majority of you put here C, right, which is transferred, which is correct, right? Because you remember, going back to my previous slide, the number was 2.5, right? And if you have a 2.5, you're right about there, right? Between 2.0 and 3.3. So the electrons are transferred. And what type of bond is that? It's ionic, right? Most commonly, that would be what? A metal with a nonmetal, correct? Right? Everybody got that? Any questions so far before we move forward? We're going to hammer this home. You better get hundreds on the quiz today. Okay? We're going to hammer this home. All right. So let's take a look at some polar covalent bonds. All right? Just some examples here. Just to show you that I'm right. I'm not just giving you BS. All right? Because I have been known to just wing these things. I really have no idea what I'm doing. But you trust me anyway because you paid for this class, right? And as long as I give you, an appropriate grade, you don't really care if I'm telling you the right thing or not. At least that's what I felt when I was in school. And it wasn't that long ago I was in school, right? So here we have hydrogen fluoride. Hydrogen fluoride, notice that it has a bond length of 0.92. Its electronegativity difference is less than 2, right? So it's what? Non-polar covalent, exactly. It's non-polar covalent, okay? And the interesting thing about that is it's barely on the cusp, right? It's almost transferring electrons, right, for hydrogen fluoride, which makes sense because essentially you have the most positive atom over here going with the most electronegative atom over there, right? So it's so close. But the thing about it is that everybody knows hydrogen is a gas, right? It's not a metal. And that's the reason why it's not like there in the ionic realm, right, where it's completely transferred. But if it were lithium, it definitely would be transferred. And so that's actually an interesting thing because if you've ever looked at other periodic tables around the world and other than in your textbooks, some people actually have hydrogen on the right side next to helium, right, because it's a gas, right? It's a gas. And it kind of makes sense to have hydrogen over here too, on top of fluorine. Why? They both have one electron that they can bond with, right? They both have one electron they can bond with. All right. Let's look at hydrogen chloride gas, right? That was the question I gave you earlier, okay? And its bond length is 1.27. It's got an electronegativity difference of 0.9. So that's clearly a polar covalent bond, right? Polar covalent. Good job to you there, hydrogen chloride gas, right? Oh, and I also forgot to talk about dipole moment too, right? Notice that there we have here with this, the dipole moment between these two, since it's so big, right? The dipole moment is very big too, right? Not so much though with the rest of these as we go closer and closer to less electronegativity difference, closer and closer. Okay. As we get to less electronegativity difference, you see that the dipole goes down, right? So those are the trends that you need to notice. Those are the trends that you need to notice. Hydrogen bromide, right? Hydrogen bromide, bromine is down here, right? So it's not as electronegative, right, as fluorine is. Does that make sense? And so that's why it's electronegativity difference is only 0.7, and since it's got a much smaller electronegativity difference, its dipole moment is only 0.28, right? Do you see the trend there? As electronegativity difference goes down, what else goes down? Dipole moment. We'll talk about dipole moment in a second. Don't worry. Okay. Also, as electronegativity difference goes down, what goes up? The distance between the two atoms, which makes sense too, right? Because the more electronegativity difference, that means the more positive one thing is, and the more negative one thing is, and the more they're attracted to each other, right? But the lower the electronegativity difference means that they're closer, right, in electronegativity difference, in electronegativity, so they're not going to be as attracted to each other. The more positive you are and the more negative you are, the more attracted you are to each other, right? But if you're kind of in the middle, you're not as attracted to each other. So, to bring it all together, as electronegativity difference decreases, you get closer to pure covalent bonding. Your dipole moment goes down, but your bond length goes up, right? I'm going to ask you questions, right, that are not going to be these elements, but there'll be other elements in the same group. So you have to understand what these trends are and these periodic trends are too, right? Okay? All right, so what exactly are dipoles? I keep on talking about these dipoles. What are those things, right? When two equal but opposite charges are separated by a distance, a dipole forms. Okay, so a dipole literally just means two poles. Di means two in Greek, by the way, di, right? Dipole moment here is actually represented by mu. Not mu2, but mu, right? I don't know if you guys noticed, but I have a Pokemon backpack. So that's, and if you're really deep into Pokemon, you know what Pokemon this is. Does anybody know what Pokemon this is? Yeah, no, it is. It's actually the three-headed dragon, Hydreigon. Yep. If it makes you feel better, my girlfriend has one too, and hers is an Umbreon, and it really looks like an Umbreon. So you can totally tell that she's got an Umbreon. And my brother has one that looks like a Dragonite. So I, of course, have the most obscure one. Okay, so anyway, mu, that's why did I even bring that up? It's because we're talking about mu, and mu too. So the dipole moment is represented by the Greek letter mu, right? And produced by two equal but opposite charges separated by a distance, right? So mu equals Q, which is the charge, multiplied by R, right? So here you can see here, by the way, the units per dipole moment is the dBs, or dBs. Let's say dBs. Big D for dBs, right? Here we have an atom that's got a negative charge, right? Like a fluorine or something, partial negative charge over there. And we have an atom over here that's positively charged, right? And the distance between, that's R. And then R, right, times Q, the charge, equals the dipole moment of M. Sure. Remember, things that are on the right-hand side of the periodic table are what? Electronegative. So if you have something like fluorine, what is it going to be charged? Exactly. But if it's on the left side, what is it? It's positively charged, right? Because metals are positively charged. That's why they're attracted to things on the right side of the periodic table, because they're negative, because opposites attract, right? Okay? So in my experience, the most difficult thing about Gen Chem 2 is connecting math with chemistry, okay? In this equation, right, mu, or the dipole moment, equals the distance between the two atoms times the charge, okay? Since both of these terms on either side of the periodic table, on either side of the equal sign, right, are not dividing, but they're on the top, right? If you recall from regular math, if you recall from regular math, when you have an equation like this and there's nothing under it, it's actually a numerator, right? And so what that is, it's mu over 1 and QR over 1, correct? Right? Both QR and mu are both numerators. So if you change R, for example, you pull two atoms further apart, right? What's going to happen to the dipole moment? It has a direct relationship, and it's going to go up, right? It would only have an inverse relationship if R were the denominator, right? If they're on the same side at the top, numerator, the variables are, you change one and the other side goes up, right? But if one is a denominator and the other is a numerator, that's called an inverse relationship, correct? Daniel, you getting this? You're just kind of staring. You're not writing anything down. So I need to know, I'm not getting any feedback from you. You're just staring. So you getting this? All right. If one term, one variable is in the denominator and the other is in the numerator, it's an inverse relationship, right? So if you make one bigger, the other one does what? Gets smaller, right? That is important. You need to know that. And there's a lot more math that happens in this class, so that's just like the scratching the surface. All right, here we go. Next question. If the charged particles are moved closer to each other, does mu increase, decrease, or stay the same? Oh, dang, that last one I was supposed to make you talk about it. I keep on forgetting to do that. I'm trying to find that equation for that one. I have too many questions I've been asking. Ah, there it is. Dipoles, I think it is? Yes. Yes, it is. All right, 12 people have responded. Let's see what everybody said. Good job. The vast majority of you chose B, right? Because I literally just said right before the question, right, that if you raise one thing on one side and the other side is also a numerator as well, as the same as the other side, then it goes up, right? If you lower one thing on one side and they're also the numerator, it goes down, right? The only way it would be the other one is if, well, for one thing, yes, the only way it would be A is if either R was in the numerator, if either R was in the denominator or mu was in the numerator, right? They have to be on different sides of the fraction sign, okay? Does everybody get that? Anybody missing that? That's important, okay? Knowing the relationship between fractions is important in an equation. Is everybody sure they got that? Okay. It gets a lot more difficult than just that. So that's why we need to make sure that we have this foundation before we start doing crazy things like ice tables and solving for equilibrium, you know. So, oh man, that was another one you were supposed to talk about. Dang it. That's okay. That's all right. What's the point of being in your houses if you don't talk about it? Dang it. I keep forgetting. I'm just getting so into the lecture is what it is. All right. So from the dipole moment, from the change or the difference in electronegativity between two atoms, from all those things, what you can do is you can describe a molecule, right, a compound, in percent ionic character. How ionic is it, right? Because before we were saying everything was either nonpolar, covalent, and then we had transferred electrons, so that's ionic. Now the descriptor is based on ionic character, right? And that's called the percent ionic character, okay? And notice here we have the electronegativity difference on the x-axis, right? And then we have the percent ionic character on the y-axis. The x-axis is always what type of variable? The x-axis is always what type of variable? Independent variable. No, the x-axis. It's always the independent variable, right? It's always the thing that you can say that you can't change, right? It's a thing that you can't change about something. You can't change the electronegativity difference between two atoms. It's already what it is. Does that make sense? Right? So the x-axis is always the independent variable. Okay? The y-axis then is what? The dependent variable, right? That means then that the percent ionic character does what? It depends on the electronegativity difference, right? It depends on the electronegativity difference. So notice, when you have electronegativity difference over here, right, between 0 and 1, your percent ionic character is what? Less than 25%. That's hydrogen chloride, hydrogen bromide, iodine chloride, hydrogen iodide, iodic bromide, right? All those. And that makes sense, again, because all these guys are lower on the periodic table, so they're less electronegative. They're not like fluorine, right? But then you jump up here, right? You have fluorine up here, all the way up here with lithium fluoride, right? Potassium fluoride, way up here. Electronegativity difference of what? Greater than 3, and they're in the close to 100% ionic character, right? And notice that it's not just based on the electronegative atom, it's also based on how electronegative atom the other atom is too, right? Because here we have chlorine, cesium chloride right here, right? Here we have cesium chloride. And cesium chloride, cesium is this right here. This is cesium right here. And this is chloride right there, right? It's not over there at the 100%, is it? It's not over there at the near the 100%. Its electronegativity difference is only between 2 and 3. Still ionic, right? But chlorine, right, is not as electronegative as fluorine is, number one, right? And the difference between chlorine and cesium is not as great as it is between the chloride of like potassium, right? Potassium chloride. Because potassium chloride is higher on the periodic table than cesium is. Remember those periodic trends? Right? Oh, man. I'm getting parched. This is getting too excited here. Okay. So I will do this again, too, where I will give you some numbers, or all you'll have is the periodic table to judge, right? And you'll have to tell me where on the percent ionic character the graph is going to be. Okay? Yes. What do you mean? Yeah. So remember that this electronegativity difference is the same as the electronegativity difference we've been talking about the entire period, right? Okay, and so these are the same numbers, right? And so the bigger the difference in electronegativity, the more ionic you are, right? All the way to the point where you're like 100% ionic, right? So these guys here, they have very little difference in electronegativity, right? So they have very little percent ionic character, right? They're not very ionic at all. They're almost covalent, right? Well, actually, they are covalent. Right? But we don't talk about it as covalent in the terms of ionic character. We just say very low ionic character right here, right? But then you go to this side over here where your electronegativity difference is larger than 3, right? And you're all very close to what? 100% ionic character, right? So lithium fluoride is an ionic compound. Potassium fluoride is an ionic compound, right? But the thing I was telling you, though, is that calcium, right here, calcium chloride, right, there's a bigger electronegativity difference between them, right? Oh, sorry. They're more percent ionic character with those two than there is between cesium chloride, because potassium chloride is higher on the periodic table than cesium is. Does that make sense? Yeah. Because chlorine is the same, right? These two are the same right here, chloride, right? But cesium chloride is only at 75%, 75% maybe, or so maybe it's like 70% ionic character, right? But potassium is up here. Potassium chloride is up here in percent ionic character, and the reason why is because potassium is higher on the periodic table than cesium is. Does that make sense? Yeah. Okay. Okay. So the question then is, like, at the end of the day, is a compound ionic or covalent, right? The easiest thing to remember is that metal plus nonmetal is going to be ionic, right? Metal plus nonmetal will be ionic. So anything from the group 1 and group 2, the alkalis and the alkali earths. It's 1 o'clock. Anything between group 1 and group 2, bonding with anything over from groups, 5 through 8, they're going to be what? Ionic, correct? Okay. But if it's a nonmetal with a nonmetal, that means things from group 5 to group 8 or group 7 bonding together will always be what? Covalent, right? The question will then be after that, how ionic is it, or how covalent is it? Is it nonpolar covalent, or is it polar covalent? Is it high ionic percent character, right, or low ionic percent character? Okay. So here's some other things. There are many exceptions, of course. In chemistry, there's always exceptions, but for now, just know these rules first, and then we can teach you the exceptions, right? It doesn't take into account oxidation numbers of metals, and the higher oxidation numbers can give covalent bonding. This only happens with this block here, these transition metals. So you don't have to worry about it, because we're not going to be talking about the transition metals right now, okay? And then electronegativity difference can be used, but the table still doesn't take into account oxidation number, of course, because we're not talking about the transition metals yet, right? The D block metals, right? Okay. And then properties of compounds are often the best, right? So lower melting point means covalent bonding, for example. So think about this. Water has a very low melting point, right? 0 degrees Celsius, right? Very low melting point. But remember what I said about sodium's melting point? What was sodium's? Yes, exactly. It's going to be over 300. Sodium chloride is like 800 degrees Celsius. Much higher melting point. Does that make sense? What does it also mean then? That means the bond between sodium chloride is stronger than the bond between water in the oxygen and hydrogen of water, right? Because it takes so much more heat to melt sodium chloride than it does to heat and melt what? Ice. Does that make sense? Right? The more bonds there are, the stronger the bond is, right? And then the more ionic it is, the stronger it is too. The stronger the bond it is too. And that's why it takes so much energy, so much heat to melt it down. You put like butter into, you leave butter outside and it will melt, right? It'll get soft and you can put it on your toast, right? But butter is made of what? A bunch of carbons and oxygens and hydrogens. And they're all covalently bonded together. It doesn't take much heat at all to break down, melt butter. But you need 800, your stove can't even get to 800 degrees Celsius, right, to melt down sodium chloride. Have you ever put sodium chloride into a frying pan and tried to melt it? No, because it doesn't, right? It doesn't melt, okay? It doesn't melt. All these have connections with each other, okay? All right, so in the last 15 minutes class, we need to learn how to do Lewis dot structures, and that's actually the last thing we're going to talk about today, okay? And after we do electron configuration in discussion, we can work on this a little bit more too. So let's talk about drawing Lewis dot structures, okay? The first thing is that you have to sum up all the valence electrons in an atom, right? All the electrons in an atom, okay? So here we have potassium, that's terrible. We have phosphorus, one of them, right? And 3 chlorides, or chlorines, right? Well, how do you know how many valence electrons there are? The periodic table, right? Your answers are on the periodic table, right? You can thank Mendeleev later, okay? Potassium, phosphorus has 5 valence electrons, because why? It's in this group right here, right? Group 5, just like nitrogen. And then chlorine, right? Chlorine has how many? 7, because it's in group 7. And there are 3 of them there. That's why it says 3 times 7, right? So that means it has 26 valence electrons, okay? That's the first step. Count up your valence electrons. The next step is to put together the atoms so they make sense. Remember that chlorine, when it becomes chloride, can only bond with one thing at a time, right? And there are 3 of them. But remember what phosphorus can do? Phosphorus is in the same group as what? Nitrogen. So it's got 3 free electrons to bond with, just like nitrogen did, didn't it? Right? And that's why you can bond 3 chlorines to a phosphorus. So just so you know now, when you have something like this and there's more than 2 things, right? Things like phosphorus will always be in the center. Things like carbon will always be in the center, because carbon has what? 4 bonds it can make, right? 4 bonds. Silicone, always in the center, right? But things like oxygen and fluorine and chlorine, those guys, 2 to 1 bonds they can make, they'll always be on the edges, okay? They'll always be on the edges. So now that you've bonded these to phosphorus in the most simple way possible, you can take away how many electrons? There's 2 there in that bond, there's 2 there in that bond, and there's 2 there in that bond. How many is that? 6. So you take 6 off, minus 6 electrons, and now you're left with 20 electrons. Now you fill in the gaps, right? The rest of them are going to be what? Lone pair electrons, okay? And if you don't have enough room, that's when you go into doing what? Double bonds and single bonds, okay? So let's see how this looks. All right, let's fill in our lone pairs. Remember, how many electrons does chlorine have? 7, right? So there's that one right there that's bonding with phosphorus, but then you got 6 left over in lone pairs. 1, 2, 3, 4, 5, 6, right? So there's 3 pairs there, 3 pairs there, 3 pairs there, right? That's 18, okay? Right? Am I right about it? 6 times 3, is that 18? Yes. Sorry, I'm hard of Asian. I'm Asian, so I'm hard of math, right? So you do that. You have 20 left over from before. You minus 18, right? You minus 18, you have 2 electrons left, right? Where do you think the last two electrons are going to go? Exactly. That's exactly right. Because remember, that phosphorus is just like what? Nitrogen. It's got some lone pairs there too, doesn't it? Right? It's in the same group. And so that's why you get that. Luckily for us, though, that we don't have anything left over. Everything fits perfectly, so we don't have to do any double bonds or triple bonds for that particular atom. Okay? It's really easy to do Lewis dot structures. You just got to count up the valence electrons, right? Draw out the structure so it makes sense, right? Draw out the structure so it makes sense. Don't do something crazy like put 5 bonds to carbon and then miss out on your PhD or something. I actually had a friend, literally. His name was Paratosh, okay? And he was defending his dissertation to get his PhD, and he literally drew 5 bonds to a carbon, and they failed him. He didn't get his PhD because of that. So don't mess that kind of thing up, okay? Which is actually kind of ironic because carbon is capable of doing this thing called hypervalence, but not in the molecule he was drawing. And that kind of error is so fundamental that you don't deserve to get a PhD in chemistry if you make that kind of error. So, yes, don't do it. I won't be so hard on you guys because you're not getting PhDs. But that guy, poor guy. Anyway, so this is going to be an example where you have to make some double bonds, right, or triple bonds, right, of a Lewis structure, right? We have hydrogen cyanide here. This is the producer of cyanide gas, the thing that kills you, right? You fill in all the electrons, but then you have 3 lone pairs here, which is fine. But the problem is that carbon is still missing what? 4 electrons, right? Carbon is still missing 4 electrons. So what does it need to do? It needs to share some more electrons with nitrogen, right? So nitrogen is like, sure, carbon, you can share electrons with me, right? Because nitrogen is so generous, right? It's going to make a bond right here. And it's going to take these electrons and make a bond right here. And now there are 4 bonds around carbon. And carbon has what? A full octet. And who else has a full octet? So does nitrogen. The same way phosphorus did, right? With 3 bonds. And an extra electron right there. Pair of electrons, right? It looks just like the phosphorus did, right? And then hydrogen is easy because what? It can only bond once, right? So this is one of those examples where you have to give it multiple bonds. The last thing you need to do when you're writing a Lewis dot structure, right, is assign formal charges. And I'll tell you why in a second. It's really simple to do this, okay? Don't think about it too much. You literally have your atom and you have your molecule, right? And you separate them with lines like this, okay? And that way you know that these electrons here on this side of the line are all belonging to oxygen. These electrons here are all belonging to carbon. And these electrons here are all belonging to what? Oxygen. And it makes sense, right? Because carbon can only bond 4 times with 4 valence electrons, right? So, and then oxygen can only bond twice with 2 electrons, right? They're not lone pairs. And so what you do is you take the number of valence electrons, oxygen has 6, right? And then you subtract it from the electrons assigned to the atom, right? And then 6 electrons are here, right? You have the 2 here from the lone pair, the 2 here from the lone pair, 1 from this bond, and 1 from that bond. So that's 6, right? Valence electrons minus the number of electrons assigned to the atom. Same thing with carbon. Carbon has 4 valence electrons. It's got 4 electrons here, so it's got a formal charge of 0. And then you're doing oxygen again, and it's also 0. That's good, because when you draw a Lewis dot structure, you want it so that the formal charges of all the atoms is 0, right? You want it so that the formal charge of all the atoms is 0. But if you were to draw it like this, right, technically you could do that, right? Because look, oxygen has an octet already right here. 3 bonds and a lone pair, right? 3 lone pairs and a bond. And then carbon has 4 bonds. That's actually full octets for everybody, right? But it's not good though, because when you figure out its formal charge, right, 6 plus 1 more here makes 7 for assigned, right? And then over here, 6 minus 5 makes plus 1 over here. So the oxygen over here is a plus 1 charge. Oxygen over here is a negative 1 charge. Oxygen over here is a plus 1 charge. That's not happy, right? A happy Lewis structure is one that is completely neutral. So which is the best Lewis structure? The first one, right? Where everything is 0. Okay? So when you draw your Lewis structures on your quizzes, on your exams, make sure you figure out those formal charges, and it's like a second check for you, right? To make sure you got the right Lewis structure. Okay? Man, we're almost done. Not always 0, but you want to be the lowest it can possibly be. Yep. Okay, so here's some more formal charge rules. Don't worry if you didn't write all that down. There's a video. Okay. So here we have I don't even know what this is called. Nitrogen, carbon, sulfur. I have no idea what it's called. Anyway, right? The dominant Lewis structure, right, is the one in which all atoms have a formal charge closest to 0, which is what I said before, right? But then also, say you can't get it to 0. Then the negative charge must be on the most electronegative atom, Okay? The most electronegative atom. Okay? So of these three Lewis structures, which one is the best? And here you go. This is your last question for today, I think. Which three are the best? You want to get close to zero. If you can't get zero, then you want to have what? The electronegative atom have the most electronegative atom have the negative charge. Excuse me. What number are we on here? House votes, untitled, bonds. What's this one called? Lewis structures, there it is. Okay, only 7 people have responded. One more person. We're missing one person. This thing will be the last thing we talk about today. And then we have discussion section at 1:30, and we have to go get you a laptop for that. Okay, 12 are in. All right, let's take a look at what everybody said. Okay. Ooh, wow. I wonder if this is one of those I'm making you talk about. It is one of those I'm making you talk about. All right, get together, talk about it. And you're ready. When you're ready with your answer, you can try it again. When you're ready with your answer, you can try it again. Remember your goal here, okay? You're trying to get to the lowest you can get, closest to zero, right? And then the most electronegative atom being negative. Okay? The most electronegative atom being negative. Talk about it. And you really need to know your periodic trends here, because all these guys are very close to each other on the periodic table. Okay? So the key here is to know which one has negative charge. Okay? And I'll give you a hint right now. It's not going to be carbon, because that's not one of the answers. So it's either going to be sulfur or nitrogen. So you've got to choose whether or not it's going to be nitrogen that's going to be mostly negative, right? Or it's going to be sulfur that's going to be mostly negative. And how do you tell? Look at the periodic table. What's more electronegative, sulfur or nitrogen, right? And the thing that kind of kills people is that they're almost equidistant when it comes to the periodic trends. But if you look at your notes, you'll see that one is more electronegative than the other. All right, let's see here. 7 people have responded. All right. Still 7 people. 8 people. Waiting for 4 more people. Yes, because the quiz is over last week. The quiz will never be over anything that we haven't already done. So it's always going to be over the previous lecture. Yes, you can. Have you been reading the syllabus? It literally says in there, on the quizzes, you can use your notes in your book. I know, I'm sorry. It's okay. All right, let's get this through. 10 people, 2 more people need to vote. Who's not done it yet? 11 people, 1 more person. There we go. All right, I am happy to report that at least most of you got this right. Okay? The answer is B, and the reason why is because nitrogen is higher on the periodic table than sulfur is. And the further up you go on the periodic table, the more electronegative you are, right? So that means that the -1 is going to be on the what? The nitrogen, right? And if you look up the electronegativity of both sulfur and nitrogen, you will see that nitrogen has the higher electronegativity, right? Because remember, as you go up the periodic table, you have a higher electronegativity. Okay? All right. I believe that our, this really sucks, but I believe that our discussion is actually in the room next door. Okay? So, meet me over there in 10 minutes. Oh, you know what? We don't even need that over there. Because I don't have any kind of, over discussion, it's just going to be, but do put your desk back together, though. Thank you so much. Put your desk back to where they're supposed to go. Thank you. I think it's, does anybody know? Is it next door or is it in here? It's next door? Dang. Why would they do that to me? It's because I'm new. Oh my gosh. I am still recording. Here I'm complaining. It's going to be on freaking Blackboard. Excuse me, on Blackboard. I better cut that part out. Oh, thank you. Thank you, thank you, thank you. Whose phone is that? Okay, just making sure you don't forget your phone. Whew, man, this is going to be a long day. Long day, long day. I will go, actually. You can stay with me and we can go together to get it. I just need to get, I need to stop the the recording before I get in trouble with all the crazy stuff I'm saying. Is it making sense to you today? Good, good. It is. But it's a good review. Yeah, because it gets